Hello guys, welcome to Magnetism, Lorentz Force and Fleming's left-hand rule. Now, what is Lorentz Force? Let's say you have a charged particle moving in a magnetic field, then that charged particle experiences some force which is known as Lorentz Force. And here the Lorentz Force is directly proportional to the magnetic field, directly proportional to the charge, directly proportional to the velocity, and directly proportional to the sine angle between magnetic field and the velocity. So combining all, we get BQV sine theta, and F is equals to K BQV sine theta, where of course K is the proportionality constant. Now, if you remember in Newton's second law of motion, where F is equals to Kma, because F is directly proportional to Ma, this K was chosen or found to be 1, so we got F equals to Ma, a very well known equation. Similarly, this K was also found to be 1, so the Lorentz force is equals to BQV sine theta. And here we can find what one value or one unit magnitude of this magnetic field is. We will have B is equals to F by QV sine theta. So let's say this is 1 Newton, this is 1 coulomb, this is 1 meter per second, and this is, let's say, just 1. So overall, B will be 1 Newton per coulomb per meter second. And here B is equals to this whole thing is 1 Tesla. And here this is for SI unit. And in CGS system, magnetic field is equals to 1 G, where G is known as Gauss. And here 1 G is equals to 10 to the power 4 Tesla. Now, we need to find the direction of Lorentz force. Now, in the mathematical way, we can find that the Lorentz force is perpendicular to the plane containing both magnetic field and velocity. So, sine theta. But here we can ignore the sine theta. Let's say that is 1. And we can write this in vector form. In vector form, well, the sine angle, cos angle, those angles don't matter that much. And in here it doesn't matter at all. So we have charge, and here even though charge there is direction, it is scalarly added, so it is a scalar. And it is velocity into magnetic field. Now here this multiplication sign matters. It is not a simple into sign, but this is in fact a cross multiplication or a vector multiplication. So according to the law of vector multiplication, this Lorentz force is perpendicular to the plane containing velocity and magnetic field, which introduces us to Fleming's left-hand rule, which can give the direction of the Lorentz force when we know direction of the velocity of the charged particle and magnetic field. And here this is Fleming's left-hand rule. There are 3 fingers, and this thumb points to the direction of Lorentz force. This index finger points to the direction of the magnetic field, so it's going like this, and this gives the velocity of the charged particle going like this. So thumb gives the Lorentz force, and the index finger gives the magnetic field, and the middle finger, it gives the velocity of the charged particle. Now, if you want to remember this, you can find some acronyms online, but the widely known acronym to remember this is, well, you have the force F, and you have the magnetic field M, and you have velocity of charged particle, so we think V. You can actually do V, but I like C, C for charge and velocity of charged particle. And here you can write, and you can remember father, mother, and child for thumb, index, and middle finger. Father, mother, child. F for father, F for force, Lorentz force. M for mother, M for magnetic field. And C for child, C for velocity of charged particle. And here at home, I want you guys to try the finding the Lorentz force due to your own directions of the magnetic field and the velocities. And here, let's say the magnetic field goes like this, the velocity goes like this, the Lorentz force goes like this from down to top. But here, let me say this charged particle is for a proton. In the case of an electron, the charge is negative, that means the Lorentz force is reversed. So if for proton it goes here, for an electron this moves down here, which is important for the electron chapter for modern physics. And here I would also like to talk about the trajectory of the velocity independent to its angle to the magnetic field. So let's say the magnetic field goes like this, and here let's say the velocity also goes like this, which is parallel to the magnetic field. Well, here the trajectory of the velocity will be a straight line. So V will be a straight line going like this. Now let's say again the magnetic field is like this, but here the velocity is perpendicular to the magnetic field. That means the angle is 90 degrees. Well, what happens is it is not a straight line, but in fact it is a circular line. So the trajectory is circular. So in fact it's more like this. And well, I guess you could kind of figure out why, because if it is 90 degrees, then the velocity and the magnetic field, when it will try to go far away, the magnetic field will pull it back, and here it will be a constant attractive force, right? Because in a circle the radius is the same, touching its all of its circumference. So that means it will kind of be like pulling the velocity towards it, which actually creates a centripetal force, which again you'll have to talk about in electron in motion of magnetic field, or motion of electron in magnetic field. And here, of course, if velocity and magnetic field makes some angle like this, velocity, I guess it would be here, then the velocity will make a spiral. If it creates an angle, it will be spiral. The trajectory will be spiral. And this is it for Lorentz force and Fleming's left hand rule along with the trajectory. So if you learned something new, please like and subscribe. Thank you.